Hello. Tonight we shall continue the study of functions by using the derivatives. Let's consider the following exercises. Consider the function f of x equals x logarithm of x, which is defined on the interval 0 infinity with values in the set of real numbers. And the questions are, first, study the monotony of the function f. Second question, prove that x logarithm of x is greater or equal than minus 1 over e for every positive x. Okay? Everything is based on the derivatives. We shall start by computing the derivative, which is given by logarithm of x plus 1. Now, the second step is to solve the equation f prime of x equals 0. The solutions of this equation are called critical points of the function f. In our case, that means logarithm of x plus 1 equals 0, logarithm of x equals minus 1, which means x equals e at minus 1, or in another form, 1 over e, which is in the domain of definition, which is positive. Now, the table of variation of the function f will be given by the domain is 0 infinity. The only critical point is 1 over e. Here the derivative is 0. Now the sign of the derivative. The derivative is this one. Now if x is less than 1 over e, for example, if it is 1 over e squared, we shall get minus 1, so here it's negative. If x equals 1, we shall get 1, so here it's positive. Consequently, the function f will be decreasing on the interval 0, 1 over e, and it will be increasing on the interval 1 over e infinity. Let's compute the value of f at 1 over e, which means 1 over e times logarithm of 1 over e, which is minus 1 over e. So here we have minus 1 over e. Now we have the monotony of the function. It is decreasing on 0, 1 over e and increasing on 1 over e. So we answer to the first question. The second one is a consequence of the table of variation. As you can see here, the value at 1 over e is the minimum value of the function f. So according to this table, f of x is greater or equal than minus 1 over e for every positive x, which means exactly what we have to prove, x logarithm of x greater or equal. Now, further, if we compute the limits at 0 and at infinite, then we can sketch the graph of the function for a better understanding of the behavior of the function. Now, limit when x tends to 0 from the right, from x logarithm of x tends to 0, logarithm of x tends to minus infinity. The usual way to compute this limit is to write it as logarithm of x 1 over x. Now this is infinite over infinite. One can apply L'Hopital rule here. And after the L'Hopital rule, you get 1 over x minus 1 over x squared, which means limit when x tends to 0 from the right of minus x. And this is 0. So the limit at 0 is 0. The limit at infinity, it is directly infinity. So this is the complete table of variation of the function f. And now by using this table, one can sketch the graph of the function. So the graph starts from the point of coordinate 0, 0, but 0, 0, it is not on the graph of the function. This point doesn't belong to the graph. At 1 over e, it takes the value minus 1 over e, so here. And then it is increasing to infinity, infinity. So the graph will be something like this. Of course, this point it's not on the graph. Okay. Let's consider another example. Now the question is to study let's consider the function on the set of real numbers f of x equals sine of x minus x at 3 over 6. And the question is to study the sine of f. That's the question. Now, let's put here plus. Okay. Now, the problem is that, of course, we shall try, we cannot find directly the sine of the function f. Instead, we shall try to use the derivative. Now, the derivative of the function, it's cosine of x minus 1 plus x at 2 over 2. And unfortunately, the derivative is useless simply because we cannot solve the equation f prime equals 0. So somehow we must accept this fact, and let us observe that, okay, the derivative f prime, it is still complicated, but it is a simpler form than the function f. So there is a hope that by using the same procedure, so by computing the second derivative, the derivative of f prime, to obtain a simpler function. Indeed, the second derivative, f second of x, will be minus sine of x plus x. Still a rather complicated function, but if we compute the third derivative, that will be minus cosine of x plus 1, which is a positive function. So the third derivative, it's a positive. It takes also the value 0 at many points, actually infinitely many points. The solutions of the equation cosinus of x equals 1 are infinitely. We can write it, but it's not important. Actually, x equals 2k pi for every integer. But we shall not use this fact. The most important it is that this third derivative, it's positive, and it takes also the value 0. Among other points where it takes the value 0, it is at 0. But not only. There are infinite many points where the third derivative takes the value 0. Now we can try to use all these results in the following way. So let's try to sketch a table of variation. Here I shall put the third derivative, then the second, then the derivative, and finally the function f. Don't forget, we would like to obtain the sign of the function f. If it is positive, negative, where is it positive, where it is negative. The domain is minus infinity, infinity. Okay, so what we can observe is that at 0, the third derivative is 0, but attention, not only at 0 it is 0. Doesn't matter. But the second derivative, it's still 0 at 0. Yes, it's very simple to observe this. Also, the first derivative at 0 equals 0, and of course the function f at 0 is 0. On the other hand, the third derivative is positive. Okay, it takes also the value 0 at different points, but that's not important. It is important that because the third derivative it's positive greater or equals than 0, the second derivative will be an increasing function. Yes. So, but we are not interested in the monotony of this function. We are interested in the sign. Accordingly to this table, the sign of f of the second derivative will be negative here because it is increasing to the value 0, and then it continues to be increasing, so here will be positive. So in this way we obtained the sign of the second derivative. Now, because on the interval minus infinity 0, the second derivative it's negative, f prime will be decreasing, and on the interval 0 infinity, f prime will be increasing. Accordingly, the sign of f prime will be on minus infinity 0, it is decreasing to 0, so it will be positive here. In the same way, on the interval 0 infinity, it will be positive because it is increasing from 0. Consequently, the function f will be increasing on the interval minus infinity 0 and increasing on the interval 0 infinity because its derivative it's positive. So consequently the function will be negative on the interval minus infinity 0 and positive on the interval 0 infinity. So we obtained in this way the sign of the function sine of x minus x plus x at 3 over 6. This is how we can use the derivatives to obtain results of this type. Okay. Let's continue another example. Let us consider the function f of x equals arctangent of x plus arctangent of 1 over x. Of course, the definition of this function, it is the union of the intervals minus infinity 0 with 0 infinity. One can observe that the domain of definition is not an interval. That will be an important fact. And the question is, the first question is to compute the derivative and then get the conclusions of the previous result. So here it's not a clear question, but only after we shall compute the derivative, we shall get an interesting conclusion about this function. So let's compute the derivative. That is a very simple question. It's elementary. Now we must know that the derivative of the function arctangent is 1 over 1 plus x squared plus 1 over 1 plus 1 over x squared times the derivative of 1 over x, which is minus 1 over x squared. That means 1 over 1 plus x squared. And if we multiply here, we shall get minus 1 over x squared plus 1. Actually, this is 0. So, interestingly, the derivative of the function f is the constant function 0. At every point, it takes the value 0. So f prime of x equals 0 for every x in the domain of definition, which is, don't forget, minus infinity 0 together with 0 infinity. And now the question is, what do we know about a function whose derivative is 0? Well, the right result here is the following. If f is a function defined on some interval, so the set I is an interval, and if its derivative is 0 everywhere on this interval, then the function f is constant on the interval I, so it's a constant function. Well, as you can see, this result, which can be applied every time when the derivative is 0 on some interval, cannot be applied in our case, because in our case the domain of definition it's not an interval, but it can be applied on each interval of the domain. So the conclusion from the fact that the derivative is 0 everywhere, it is that on the interval minus infinity 0, f of x is a constant, C1, and on 0 infinity, the function f is again a constant, but not necessarily the same constant can be. So on the domain of the definition, our function is not a constant function necessarily. We shall see if it is, it could be, but not from the theory directly. So now let's compute these constants. On the interval minus infinity 0, let's take x equals, for example, -1. And f of -1 will be r tangent of -1, which is minus pi over 4, plus the same. So it is minus pi over 2. So on the interval minus infinity 0, it is the value of the function, which is a constant. It is minus pi over 2. At x equals 1, the value of f at 1 will be pi over 4 plus pi over 4, which is pi over 2. So on the interval 0 infinity, the value is constant, but it's pi over 2. So the two constants are not equal in this case. So what we did prove is that following, that r tangent of x plus r tangent 1 of 1 over x equals minus pi over 2 for every negative x and pi over 2 for every positive x. Okay. Let's consider another exercise from the same type. So here what we are doing is to see how we can use derivatives to study functions. Let's consider now an exercise where we have a module, of course. Let f of x be e at module of x over x plus 2. Of course, the domain of definition, it is minus infinity minus 2, together with minus 2 infinity, taking values in the set of real numbers. And now the question is to find the local extrema. Now, when we have functions with modules, the first step is always to explicit the module. So actually our function will be written as e at minus x over x plus 2 if x belongs to minus infinity minus 2 together with minus 2, 0. The function is defined at 0. We shall put here a closed interval, and e at x over x plus 2 when x belongs to 0 infinity. Attention, at minus 2 it is not defined, but at 0 it is defined. Okay. And now we shall start to study the function. F is continuous simply because the module is a continuous function. So we don't need to check the continuity. It is continuous at 0, of course. And in all the points of the domain of definition, it is continuous. Now, the problem with the derivative. Of course, if x is different from 0, f prime exists, and we shall compute it. So the next computation, for the moment, has a meaning if x is different from 0. So let's compute the derivatives on each interval. When x is negative, we need to compute the derivative of this function. And this will be equal to minus e at minus x times x plus 3 over x plus 2 squared, while e at x over x plus 2, the derivative here will be e at x times x plus 2 minus e at x over x plus 2 squared, which is e at x times x plus 1 over x plus 2 squared. So this is for negative x, this is for positive x. So the derivative will be as follows. It is minus e at minus x times x plus 3 over x plus 2 squared. If x belongs to minus infinity, minus 2 together with minus 2, 0. For the moment at 0 it's open because we don't know yet if the function has a derivative at 0, so it's a squared. And below we have e at x over e at x times x plus 1 over x plus 2 squared if x belongs to 0, infinity. Now what happens at 0? Let's compute the derivatives from the left and from the right. The derivative from the left at 0 will be the limit at 0 of this function, which is minus 3 over 4. And the limit, while the derivative from the right will be 1 over 4. So the two are different. So the function is not derivable at 0. This is called an angular point. Okay, now we need to compute the critical points, which gives us x equals minus 3 on this side. The next one gives us x equals minus, but it doesn't belong to 0, infinity. So we have only one critical point, which is minus 3. So the table of variation of the function will be x f prime f. The domain is the set of real numbers without minus 2. And we obtained critical point minus 3, here is 0. And at 0, which is here, the function has not a derivative. And now we shall see the behavior of the function, more precise, the monotony. So the derivative is written here. On this interval, when x is less than minus 3, this is positive. Here it's negative. On minus 2, 0, it's again negative, and on 0, infinity, it is positive. So the function is increasing, decreasing, decreasing, and increasing again. We need to now to compute the values at minus 3 and at 0. Anyway, we can answer from now that x equals minus 3, it's a local maximum, while x equals 0, it's a local minimum. So we know the local extrema and their nature. Of course, if we compute the limits and so on, we can sketch the graph, but the question was just to compute the local extrema. Okay, thank you.